Here we are using the numbers a, b and c in such a way that a is equal to 2x plus 1, b is equal to 2a plus 1 and c is equal to 2z. We can substitute these into the equation a square plus b square is equal to c square to get 2x plus 1 whole square plus 2y plus 1 whole square is equal to 2z square. So 4x square plus 4x plus 4y square plus 4y plus 2 is equal to 4z square after expanding 2x plus 1 whole square and 2y plus 1 whole square. Now divide by 2x square plus 2x plus 2y square plus 2y plus 1 is equal to 2z square. This last equation says that an odd number is equal to an even number, which is impossible. So a and b cannot be odd. Since we have just checked that they cannot be even and cannot both be odd, it must be true that one is even and the rest two are odd. It is then obvious from the equation a square plus b square is equal to c square that is c is also odd. You can see we have just put here a, which is odd number, b which is odd number, and c is even number. In first experiment we have used a and b odd number and c is even number. We can always switch a and b. So our problem now is to find all solution in natural numbers to the equation a square plus b square is equal to c square with a odd, b even, a, b, c having no common factors. The tools that we use are factorization and divisibility. Our first observation is that if ABC is primitive Pythagorean triple, then we can factor a square is equal to c square minus b square is equal to c minus b into c plus b by the factorization of c square minus b square. Here are a few examples from the list given earlier. We had note that we always take a and b odd and b is to be even, like 3 square is equal to 5 square minus 4 square is equal to 5 minus 4 into 5 plus 4 is equal to 1 into 9. Same here 15 square is equal to 17 square minus 8 square is equal to 17 minus 8 into 17 plus 8 is equal to 9 to 25. Same here 35 square is equal to 37 square minus 12 square is equal to 37 minus 12 into 37 plus 12 is equal to 25 into 49. Same for 33 square, 65 square minus 56 square is equal to 65 into 56, 65 minus 56 into 65 plus 56 is equal to 9 into 1 to 21. It looks like c minus b and c plus b are themselves always squares. We check this observation with a couple more examples, like 21 square is equal to 29 square minus 20 square, which is equal to 29 minus 20 into 29 plus 20 is equal to 9 into 49. Same for 63 square, 65 square minus 16 square is equal to 65 minus 16 into 65 plus 16 is equal to 49 into 81. Now we can prove that c minus b and c plus b are squares. Another observations apparent from our list of examples is that c minus b and c plus b seems to have common factors. We can prove this last assertion as follows. Suppose that d is a common factor for c minus d and c plus b, that is d divides both c minus b and c plus b. Then d also divides c plus b plus a c minus b and is equal to 2 times c, and also c plus b minus of c minus b is equal to 2b. Thus d divides 2b and 2c, but b and c have no common factor. This is very important result to understand that d divides 2b and 2c, but b and c have no common factor, because we are assuming that ABC is primitive Pythagorean triple. So d must equal to 1 or 2, but d divides c minus b and c plus b is equal to a square, and a is odd, so d must be 1. In other words, the only number dividing both c minus b and c plus b is equal to 1. So c minus b and c plus 1 have no common factor.